right, good afternoon, I guess. Yeah, afternoon. So, hopefully everyone is done with at least setting up lab one. So, okay, come on, we're starting. Little countdown's already done. So, hopefully you've already set up lab one. If you haven't set up lab one yet, I suggest that you do that. The record for the practical session to get someone running on an old version of Windows 10 was like 10 Windows reboots. So especially if you're on an older version of Windows 10, you should, if you haven't done so already, try and set up the lab environment and make sure it works. Otherwise, if you're struggling to set up the lab environment and it's due on a Monday and it's a weekend and the rest of the teaching staff tries to have like a little bit of a life, then you might be screwed, so don't do that. So today we're going to talk about more process practice, get used to it. We'll do some more fun examples today. Some of you might have noted there's only a few slides today, so most of it's code examples, and we'll go ahead, run some stuff. Make sure we really do this. At the end, we'll do some like sample exam questions that they even had last year, and hopefully we'll understand it a bit better. So yeah, first note of advice, I'm going to try and move the midterm to Tuesday, the day before on February 28th. So there seems to only be one major conflict with that. Otherwise, most of you already have an exam on March 1st, but the schedule I got says you guys are free on that week, so I guess that's not true. So I'll try and do that, try and move it to a better room that doesn't have the crappy side table thing, because those are awful. So we'll see where I get at with that. So if that presents a bigger problem, let me know. So far it seems that might be better. And I'll probably just move my office hours to Tuesday too to get the advantage for that. So the last thing I didn't mention in the last lecture when we were talking about signals and them being user interrupts, well, I should talk quickly about like hardware interrupts like on your actual CPU that we won't encounter, but you should know about. So on a RISC-V CPU, this is the model for most other CPUs, or there's something similar to that. There's actually 3 different terms for interrupts and different types. So there is an interrupt, which is something that's triggered by external hardware that might be generated by like your keyboard or a network device or something like that. And that's like some external source generates that, and then you have to handle. And we know that the kernel is the thing that interacts with the hardware, so the kernel would have to interact with that. And the nice thing about interrupts as opposed to polling is, you know, if we need to respond quickly, we respond as quickly as possible if we use interrupts. Then there's something that kind of behaves like interrupts called exceptions, and they're not like C++ exceptions, they're hardware exceptions. So they're generally kind of like interrupts, but they're triggered by an instruction. So if you try and do like a division instruction, one of the exceptions you might generate is if you try and divide by 0 or something like that. If you try and access some illegal memory corresponding to that instruction, and the default handler is going to be the kernel, where whatever process made that instruction gets suspended, the kernel would get the exception and then choose what to do with it. And one thing it can do is optionally kind of translate it into a signal and let the user process handle that. So you might get an illegal memory access, it would generate an exception on the CPU, the kernel would get that, and then maybe it sends a SIG fault to your process, and you can actually handle a SIG fault if you want, and actually try and recover from it, or do whatever. That's one of the options you have. Or you could do like we saw in the last lecture, where we just kind of ignore SIG faults, but likely that's not going to get you anywhere, because it would just try the instruction again, and it would probably fail again. So those are the 2 reasons. So an interrupt, so that's something from hardware, or an exception, which corresponds to an instruction. And then there is a trap. So a trap is essentially the interrupt handler. So a trap is just when you transfer control because of either an exception or an interrupt, and it's the code that runs or the handler. So a trap would, either of those could generate a trap where the kernel runs some code to handle that. So in this case, a system call would be, it's an instruction, so it would generate an exception, and then that handler would be in the kernel, and you're kind of requesting it. So it could be considered something called a requested trap. So I want the kernel to run some code for me. So that's a little bit of terminology for the actual hardware. So today we'll introduce a new API. So this will complicate our lives with processes and make sure you really understand them. So the new API is called pipe, and it is just a simple system call that takes, it might look a little bit weird, but it just takes an integer array of size 2. So it just wants an array of 2 integers and then returns an int, and that int is basically either 0, where it created 2 file descriptors, or -1, where it didn't create file descriptors. And then it's going to set error no, like we know and love. So what pipe does is it will write values to that integer array for 2 file descriptors, and it essentially forms a one-way communication channel using 2 file descriptors. So you get 2 file descriptors out of it. So pipefd, the array at index 0 would be the read end of the pipe. So you're allowed to do system calls, read system calls to that end of the pipe. And there is these 1 index, and that is the right end of the pipe. And the way the pipe works is whatever you write to the right end of the pipe will be read from the red end of the pipe, which seems kind of useless if it's one process, but this is one way to do inter-process communication. And you can think of the pipe as like a kernel-managed buffer that the kernel manages, so 2 processes are able to talk to each other. It handles, setting aside memory for that, where it lives, all that stuff under the hood where you don't have to worry about it. And your interface is you write to one end of it, and then you can read from the other end of it, and you'll get the data sequentially out of the other end. So, oh yeah, first, I'll do a quick aside. So we kind of saw that, we can fork and create a new process and just let it run. So you can actually use your shell to create a new process and not wait on it. So have it return immediately. And that's using that ampersand sign. So if you use ampersand at the end of the command on your shell starts that process and just returns instantly and kind of lets it run in the background, and it will tell you when it's done. So if you do like sleep 1 with an ampersand, so let's go and do that quick. So if I do sleep 1 with an ampersand, it returns immediately and tells me that process ID that it just created, and then lets me type on the terminal again. And then eventually when it's done, it's going to say, hey, it's done, and it's done. I mean, that's pretty much it. So what you can do with that is we can kind of create a fork bomb. So that pipe character will create a pipe between 2 processes where the standard out of one, it goes to the standard in of the other. So one writes to the right end of the pipe, which would be whatever's on the left-hand side, and then the other process reads from the read end, and it replaces standard in. So remember we talked about a fork bomb before, where you just kind of exponentially create more and more processes? Well, in Bash, you can create a command that will fool your, maybe your friend, maybe your not friend, into essentially fork bombing themselves, and that's what this does. So this looks just a bit weird, and it's meant to be something you like kind of copy and paste. That's why there's this warning, do not run it. So what this actually does is defines a function called just colon that takes no arguments, and what colon does is create another version of itself and then pipe it to another version of itself. So every call to colon creates 2 more processes that just communicate to each other, but they don't have to. And then this ampersand sign throws them off in the background. And then semicolon just means I want to do another command again. And then this semicolon just calls the function once. So this would call the function once, which creates 2 processes, and then it would recursively call itself over and over again. So that process would create 2 more processes, and each of those would create 2. And that's a way to fork bomb your friends without doing just like the explicit while true fork in a C program. So I feel like that needs to be like in every operating system course to understand that, but do not run that command. So let's get into kind of the main example for today. So we're going to look at the pipes.c. It's in the examples repository. So let's go ahead and see that. So in pipes, let's look at that. We're just going to write a little helper function here because we're going to make a bunch of other system calls that basically just checks if the return, so we'll just always give this the return value of whatever our system call wrapper is. So it will check if it's not -1, that means there's no error, so we're all good, so it'll just return. Otherwise, it will capture that error no, print whatever the error is, make sure that p error doesn't overwrite error no, and then just exit with the status, equal to that error code. So just in case anything goes wrong. So here's our main function. Do I need to make that bigger? Probably. Okay, so here's our main function. So it creates an array of 2 integers and then calls pipe. Whoa, that's huge. Then calls pipe with that array and make sure that it doesn't have an error. So if I get to this point, it means I have 2 valid file descriptors. So I have fds0, which is, the read end of the pipe, and then I have fds1, which is the write end of the pipe. So I'm going to have that. I'm going to have 2 file descriptors. If by default, I already know what numbers these are, I could probably guess. My standard file descriptors, as we all should know, 0, 1, 2. So the rule is it would use the next lowest available number. So this is probably file descriptor 3, and this is probably file descriptor, 4. So whenever we fork, again, review, it's exact copy, 2 processes exactly the same. The only difference is going to be the return value of fork. So at the point of the fork, there are now 2 extra file descriptors open, so both processes will have all those file descriptors. So the parent and the child will have file descriptor 3 and 4, which are the read end and the write end of the pipe. And the only difference is going to be the return value of fork here. The PID will be greater than 0 if it's the parent, and you'll have the process ID of your child, and the child, it will be 0. So hopefully that is clear. I don't see questions about that. Then we're going to check, make sure that fork actually worked properly. And then if it did, we'll do something kind of tricky. So in the parent, we'll just create a string called hello howdy child. I don't know why we're like Texan today, but apparently we are. And then just compute its length. So we'll get its length. And then we're going to write some bytes. So we'll write some bytes to the right end of the pipe. So we'll write to fds1, and then the buffer will be pointing to that string, which is just a bunch of ASCII characters. And then we're going to tell it to write however many bytes are in that string, and that's it. And then we'll just go ahead and check that our write system call actually worked correctly. And if it didn't, the process would exit, but hopefully it works. And then in the child will do something completely different. So the parent, all it does is write a string to the right end of the pipe, and that's it. So I'll scroll down quick to show that at the end of this if else, all it does is close the file descriptors representing the pipe and then return 0. So it would just exit 0. So all the parent does is write. Now, all the child's going to do, it's going to create a buffer, and that's only in the child, and it would do a read system call. Okay, stop that. Okay, it'll do a read system call to the read end of the pipe and give it the buffer, and however many bytes are in the buffer, it's that magic 4096, which we'll see why that is later. And then what it will do is check if there's any error, and then if not, it will print F, and this looks like a bit of a weird string format. You might be used to just &S. So this, I didn't send a C string, I didn't send a null byte or anything, although I guess I could have. But if you don't send a null byte, what this will do is say, hey, the period is just I want a width and then the star means I will give the width as an argument. So I won't use a C string at all. So I'll tell it, I want you to, output a string of bytes read length. So read that many bytes, and my string is just going to be the buffer. So it doesn't end in an all character because I don't know, I just didn't feel like it. And then that's it. So anyone want to tell me what I see when I actually run this program? Or easier first question, how many processes get made? 1. So I start executing main, and it forks once and creates one more process. So while it's running, there's 2 processes, the original one and the newly created one. So what should I see as output here? Does the parent output anything? Let's go up. Oops. So does the parent output anything? No, it shouldn't, because it's just writing to the right end of the pipe, which isn't our terminal, so we shouldn't see anything. And then will the child print anything? It should print out child read, and then what should it read? Yeah, it should read howdy child if this pipe works how it probably should work. And that's actually a form of inter-process communication. Yep?
Where did the parent write to the buffer?
So the parent wrote to the buffer right here. Whoops. So it did a write call to FDs 1. And FDs 1 was the right end of the pipe.
Sorry, but I thought in like the else, we initialize another buffer.
Yeah, so in the so the parent won't go into the else, right? So from the fork, the parent will get a process ID greater than 0, and the child will get a process ID less than 0. So say we create, I don't know, process 101, then the parent would get 101 as the value of that PID, and the child would get PID equal to 0 because it's a child. And then we have 2 things executing at that point. So the parent's only going to go into this if branch and execute this code, and it wouldn't go into the else because it went into the if.
I thought the parent and the write, I thought we are writing into str, but then in the read, we're reading from like the variable called buffer. Does it not matter?
So we're just writing that string. So that string is just pointing to a bunch of bytes because it's C. So we're just telling it to write that string to the right end of the pipe.
Okay.
So we're writing that string out, and then we don't know what we're reading, so we just create a buffer of some bytes that the kernel can go ahead and fill that information in with data. So you can kind of think the kernel is doing the opposite thing. So for a write system call, the kernel has to read the bytes we have there, and then for a read system call, the kernel has to write the bytes to that buffer. So what happens to the buffer is actually the opposite name of the system call. Okay, so let's go ahead and, so if we do that, yeah, it actually works. So the child, all it does is read, and it gets information from the parent, right? It doesn't read some string. That string only exists in the parent because it's in that if branch, and the buffer only exists in the child. So I'm using a pipe, and the fact that fork copies everything, including all of the file descriptors, to be able to essentially share a file descriptor. So I create a pipe, I forked, and I said, hey, parent, you write to it, child, you read from it, and then since those are 2 different processes, they get some communication. Yeah?
Is there a concern that the parent might write after the child reads? How do we know that the writing is going to happen?
So the question is, how do we know the write's going to happen before the read? Is that?
Yes.
Okay, so for that, so we do have to argue about both, but read is going to block. So what could happen after we fork, we don't know what's going to run first. if the child runs first, it would create the buffer and then do a read system call before we write anything. And that's okay because read is blocking. So read will sit there and the kernel won't return until there's actually something to read. So it'll sit there. If it happens to go first, it's fine. Doesn't matter because read is, what we call a blocking system call where it's not going to return until it actually gets some data back out of it or that file descriptor gets closed or whatever. Was that the other question too? Yeah.
Can you use pipe to communicate between two different applications that aren't like forms of each other?
That aren't what, sorry?
That like one isn't the child of the other?
Yeah, so the question is, can you use a pipe to communicate between things that aren't related, essentially? And the answer to that is no. So you're only able to share this file descriptor because of fork copying everything. Otherwise, you can't just create a file descriptor that just there's no way to get a pipe back unless you have a name for it or something like that. So there are other forms of IPC that essentially take a name that you can, other processes don't have to be related, but pipes, they have to be related because they only get shared through fork. Yep.
Like, isn't it like two processes as long as they get like the same, like the pairs of file descriptors is going to work fine, or you have to share everything like using fork?
Yeah, so if you create the pipe like after the fork, then you can't share because each process would have created its own pipe. So this, I can only share because I created a pipe before I forked, and then they both got copies of it. Or I guess the newly created one got a copy of it, the parent always had it. So any other questions about that? Yeah.
Not really about the code, but how are you getting those like smaller text that like seems to be the name of the argument?
Oh, so that's Clang D, which was the recommended thing for the lab setup. So if you do the recommended thing, you'll get arguments like that. Okay, so let's do something fun that will test our knowledge of, orphans and zombies and all that. So this is kind of related to that question of like, how do I know that write happens before the read? Okay, well, one thing we might have a question about is like, hey, what if the parent doesn't write at all? What do we think is going to happen if I do something like this? So the parent doesn't write to that buffer, and the child just wants to read from it. Anyone hazard a guess as to what would happen here? Yeah.
Doesn't the parent stop executing because it goes to the end of the program, and then the child can become an orphan or zombie or something?
Yeah, so what will happen, so let's argue about the parent. So in the parent, same thing, it's going to set up the pipe, then fork, so now it creates a new process. And now in the parent, it does nothing, and then it would go ahead, close the ends of the pipe, and then return 0, which is the same as exit. So now the original parent process is now kaput, it is terminated, and we have essentially created an orphan. So our child is going to be an orphan. It's going to get reparented to something. Is it going to still exist, or is it going to die as well? So what happens to our poor orphan process when it gets reparented? Is it still running, or does it die, or what happens? Yep.
I think system D or init, I forget which, will kill it.
So the guess is system D or init will kill it. So system D or init would call wait on it. So would that necessarily kill it? No. So it should, system D would inherit it, but it wouldn't kill it itself unless it was like bloodthirsty for some reason, because it's just a program. Someone could have written it that way. But by default, it just kind of waits. Okay, well, I guess let's just run it and see. Whoops. So if I do that, returns immediately because my shell only cares about the parent. So I create an orphan. I don't even know what process ID is created, but I can go ahead and run a command that will get me the process ID of everything with a matching name. And if you've done lab 1, you could probably have written this program yourself. So it's called PID of, and then you give it a name, and it will tell you if that program still exists. So if I do PID of pipes, oh crap, it's still alive. So my child is still actually running. It's not a zombie or anything. Well, I actually don't know if it's a zombie, so I can go ahead and check. Proc 1992 status grab. Whoops. State. Yeah. Okay. So I see that it's there and it's sleeping. So what is actually happening is something strange. So it's still alive and it's kind of just waiting. What is probably sleeping doing? Anyone hazard a guess as to what it's actually sleeping on? Yeah. Yeah, so it's actually just stuck on this read call. So we can even verify that to be like, hey, printf, so if we do that, let's, anyone want to tell me how to violently murder this process because I don't want it running anymore? Yeah. All right, kill -9. I'm sick of it. All right, so now it's gone. So I cleaned it up. And then I'll go ahead and run pipes again. So I see before read, I don't see after read. So it's still in that read call. It is reparented to whatever systemd in this case, and it's sitting there blocking on read. So why that is and why some of you already asked in lab 1, it's like, why the hell do I have to close my file descriptors? Won't the operating system clean it up for me? Well, in this case, the operating system's not terribly smart. So what it will do is for a pipe, read will return 0, which means there's no way to get data into the pipe, only if nothing can write to that pipe, which something can write to that pipe if they have a file descriptor open to it. So my process that created the pipe doesn't have the right end open to it because, well, 1, at the end of this else statement closes both ends of the pipes, and then it exits, but it would have got cleaned up anyways when it exited. But unfortunately, in the child also has the right end of the pipe open and the read end of the pipe open, even though it never uses the right end of the pipe. So because it has the right end of the pipe, the kernel just assumes that maybe it could write data to itself. So read, I'm not going to return 0 because it's possible, although maybe unlikely, that it will actually get some data written to it. So we can actually clean up our child if we do something like this. So if we close the right end of the pipe when we're done, or when we're done with it, and then close the other one after we're done reading from it, and then I will just move this up to the parent so we don't double close ourselves, even though it doesn't really matter. So if I go ahead and do this now, I won't create that problem. So let me kill this. So that's my child that's just kind of still waiting on something, and I cleaned it up. So if I go ahead and do this now, I see, hey, I might have created an orphan. In this case, I don't know what ran first or what not. But because I actually closed the right end of the pipe, and the kernel now knows it's not possible for no process has the right end of the pipe open, so read will actually return 0, and then I print out, hey, I read 0 bytes, so child read just shows nothing. So this is a one very important reason why it is like really, really important to close your file descriptors when you're done, because that's how it works. So any questions about that? Okay, so yep.
So just to clarify, if the child has nothing to read, it just can't read anything?
So in this case, yeah, if the child is not possible to get any data into the pipe, then read would just return immediately with 0 bytes read, indicating that it's not possible to get any more data, so you're done. So now we know why there's no like end of file character, because it could represent different things. So read returning 0 just means it's not possible to get any output or read anything more. So that could be end of file. That could be that no one can write to the right end of the pipe, so I can't read anything. So you can see why they made it really abstract, because there's multiple reasons why you can't read anything anymore. Yep.
Sorry, I'm still not sure. Is this two-way? Like, could the child write something back afterwards? Or is it only one way?
Yeah, so this is only one way. So anything you write will come out the read end. So if you want two-way communication, you need 2 pipes. So I could make this that I create 2 pipes up here, and then in the child, I write to one of the pipes and the parent reads from the other end, and vice versa for the other process. So that's how you get your two-way communication. It's just 2 pipes. Okay, any other questions before we move on? Yep.
So if we didn't close the FPS1 in the parent,
Yeah.
then the process would keep running.
So in this case, so the question is, if I didn't close the FDs in the parent, would it still run like that? And in this case, it doesn't matter, because when your process ends, it will close all the file descriptors. So if I just didn't have these lines, well, in the parent, all it does is just return 0, which would call exit, which would close everything, because that process is now dead. So I actually didn't need to have them there. It's just kind of like a good habit to get into. Just close it as soon as you don't need it anymore. And then that's as soon as I don't need it anymore. So if I did close them before the fork, well, fork is a copy at the fork. If I close them before the fork, then they're closed in both of them, so the other one wouldn't ever see it. Okay, so let's go back. So yeah, so that's some basic IPC. We'll see more of it as the course goes on, but that's like really basic ones, and most of the mechanisms will still be the same read and write thing. It's just how you get that file descriptor essentially is the only thing that changes. So we saw kind of, you could redirect some file descriptors for communication, as we saw before with like that open stuff, and then saw some signals. So this is recapping on last one too. So signals were like interrupts for user processes, and the kernel has to handle things more complicated. There's like 3 different kinds of interrupts, so just remember, exceptions related to instruction, interrupt from hardware, and a trap is the actual code that runs. So let's look at some finals from last semester. So one of the things people like doing is making sure you can understand and follow what processes could be running when. So it says for each program below, state whether it produces the same output each time it is run, or whether it produces different outputs each time it is run. So basically, if it's constrained to be at a set order, or if it's not, and then explain why the program behaves like this. So here's our example. I'll leave that up for a little bit and let you think of that, and then we'll go ahead and argue about it together. Oops. All right. Anyone have any guesses as to what this might do? Yeah.
I don't think you can guarantee it'll print the same every time, because what happens is if in the parent fork, or in the parent process, it will print I and then exit. But in the child process, it will simply decrement I, go back in the loop and fork again. And you can't guarantee if when it forks, the child or the parent runs first. And if the child runs first, then when it forks again,
Yep.
it will print first. It will print before its parent prints.
Yep. Okay. So we'll go through it. Yep. Yeah. So the answer, we have a bunch of print 4, 3, 2, 1, but don't know what order. Yeah.
Just a quick question for the int I equals 4 here.
Yep.
Since we're creating the child process after it, does it still create a copy, or is it referring to the same variable in memory?
So fork, remember, it's a copy where both of them after the fork look exactly the same, but they're completely independent.
So then does the child affect the parent in this case?
So in this case, two processes do not affect each other ever, unless you kind of opt into it. Yeah.
Would it not just print 4
Yeah.
4 times or 5 times?
Oh, okay, so one possible solution is print 4 times. Okay, so let's go through and argue about it, see if it's in order or what. So here's kind of what it looks like. So initially, I'll give processes PIDs. So I'll say the original one, just for argument's sake, is PID 100. So PID 100 is going to come, it's the only program, or it's the only thing executing, and it's going to start main and start executing. It's going to create int I equals 4. And then after that line, that would be allocated on the stack or something like that. Well, it would be. And then it would go into that while loop. So the while loop is now while I does not equal 0. And here I'll write in as well in PID 100, I equals 4. Since that's the main thing I care about. So I'm going to go into the loop because I does not equal 0. And then I'm going to fork. So in the fork, I'm going to create a new child, and I'll write out what the two things are. So in the parent, the return value of fork is probably going to be a new parent. I'll just use the next number just for argument's sake. And then in PID 101, well, it's an exact copy at the time of the fork. That includes the value of I. So in 101, I is currently 4 because that's what it was at the time of the fork. And PID is going to be equal to 0 because it is the child. And now they are both right there, right after the fork. So we're both good right now. There are two processes right after the fork, same I value, same everything. At this point, we don't know what's going to run first, so we have to argue about it. So if the parent runs first, which is PID 100, what's going to happen is it will check this if statement is not true. So it would come in the else and then print 4 and then exit, and now it's done. So this would have print 4, and now it is kaput. But that didn't need to happen because there's nothing preventing the other one from running first. So it could have printed 4 first and then went kaput. Or in process 101, we would have come in here, decremented I, and it's independent. So it would have changed only the value of its I. Oops. So now in that process, I equals 3. And it doesn't affect the other one. 1, well, there's independent because of the fork. They should be independent. And 2, well, the other one could could have printed 4 even before that happened. So any questions about that part? So just remember they're independent. So what's going to happen here is, in this case, it would have went into the if statement, decremented I, which we did, and then go back up into the while loop. I is not equal to 0. Then it would fork again. So in this time through fork, fork's going to essentially overwrite that process ID. So it would create a new process, probably called process ID 102, and exact copy at the time of the fork. So in that process, what was the parent's value of I? 3. So what's the child's value of I? 3. And then in this case, we'd be overwriting the PID. So in process ID 101, that fork would have overwritten it. So PID is now 102. And in 102, PID would have been equal to 0. So any questions about that? So now they're both right here, right after the fork. And then, yep.
So for 101, the original return PID equals 0 just gets overwritten by the second fork?
Yep.
Okay.
Yeah, because that would have been out, well, in this case, it would have so PID would have been dead by the time it exits this loop, and it would have got reallocated when it gets back to that loop. So, but it would be the same address. But if you want to think of it kind of more theoretically, well, I should have, I guess, erased that PID equal to 0 in 101 when I went back in the loop, and then created a new PID because it would have allocated it at the beginning of the loop. So yeah, good point. I kind of skipped a step. So in this case, we still don't know what's going to run first. In this case, we could process ID 101 could execute first, and then it would go into the else statement, go ahead and then print 3, and then it's dead. So in this case, was there anything to prevent 3 from happening before 4? No, because what could have happened is, well, process ID, when they forked and created process ID 101, I could have just executed 101 and let it run. It would have created 102 and then printed 3 and exited. So there's no ordering between them. They could have happened at any time. So in this case, what's going to happen in process ID 102 is it's going to hit this if branch, hit I minus minus, so it would decrement I. So I is now equal to 2. And you could see how this could be a real mess if that I wasn't actually independent for each process. We wouldn't even get 4 every single time. It would just depend, if that was actually shared between all of them, it just depends who gets to it first. So you'd have no way of even knowing, like the outputs of the processes would all be completely different. So, so process ID 102 would go ahead, it decremented, and it would go back to the beginning of the while loop. So I'll do the right thing and just say when it gets to the end of the loop, it would have just removed that PID, and then it would allocate a new one. So now I have a fork again, and I'm going to create a new process called PID. I'm going to assume I'm going to call it 103. And what's its value of I? Hopefully. Anyone value of I? 2. So exact copy at the time of the fork. Right now, process ID 102 called fork. Its I was equal to 2. So process ID 103 would have I equals to 2. And then the only difference is the value of PID. So this one would be 103. And 103, since that's the new one, its PID is equal to 0. So if 102 decided to execute, oops, sorry, I'll move this first. So they're both there. So now if 102 decided to execute first, it would go, PID is not equal to negative, or not equal to 0, so it would go into else, and then it would go in this graveyard down here, where it would go ahead, it would have printed 2, and now it's dead as well. Oops. So now it's dead as well. So now the last process remaining is process 103. So what it would have done is it would have checked when this loop I is equal to 1. So it would have decremented I, then went back up to the top of the loop, removed PID, and in this case, I is not equal to 0. So we'd go ahead, fork again, creating process ID 104, which is the exact copy, so I would be equal to 1 in this case. And the new PID in 101 would be 104, and 104 PID would be equal to 0. In this case, same thing is going to happen. 103 would print 1 and then die. And then in 104, well, what 104 is going to do, whoops. So 104 is going to check the process ID, it's equal to 0. So it would go, or it would, yeah, process ID is equal to 0, so it would decrement I. I is equal to 0 now. Then it would go back to the top of the while loop, check the condition, now I is 0, so it wouldn't execute, so it would just die and not print anything. So we would get 1, 2, 3, 4 printed in no particular order. So any questions about that? It's like fairly complicated, a lot of things are going on, but the principle is, hey, copy exact time of the fork. Yep.
So let's say you have PID 100, and then you create a top process of PID 0, and the next iteration you have top process 101. Is that the child of PID 0?
So in this case, there's only one kind of hierarchy of processes. So my original process 100, so only the child creates a different process because here the original parent immediately prints and exits. So 101 would have created a child called, 100 would have created a child called 101, and then 101 is the one that created 102, and 102 created 103, and then 103 created 104. So the PID is 0 that's the PID that the child sees, the newly created process sees. So in this case, if I come in and start executing with process 100, if this is the only process running, it's going to go ahead, get some space for 4, and then call fork. And then fork creates a new process. So fork would create process, whoops, that's not. Fork creates process 101. And then the way fork works, the only way to differentiate them is the return value of fork. So in process 101, that variable would be equal to 101 because that's the process ID of the newly created process. So that's your child. And then in process 101, PID equals 0 because it's the child process. And that's the only way to tell which one's which. All right, any questions about that? So what you can do, or we can follow up on the Discord too, is you should understand also this one. So same question, except now there's a wait PID before the print. So Oh, can't see. Okay, same. Whoops, wrong one again. All right, so it's the same thing, except there's like a wait PID instead of the print. So we can take it up in Discord, but just so there's a record of it. This should always print in the same order, 1, 2, 3, 4. So you can take it up or ask questions if that is unclear. So just remember, pulling for you. We're on this together.